Welcome to another GC Basic demonstration. This is part 10 for the PICK18xxQ24 chip family series. So this is part 10 EEPROM operations, and I'm going to touch on some other stuff as well, but it's focused on EEPROMs. Please like and subscribe, watch it all the way through, and give us a thumbs up. Thank you. So this is showing some values that are from the EEPROM. So we're going to program the EEPROM, read that back, and we're going to put on the serial terminal. And we're going to look at some of the constants that you might want to use. After that, we are going to go into more display GLCDs and then into more signal generation. It gets more complex, so we're building up nice and slowly. So I'm assuming you've got your software installed, you've got your programmer attached, you've got a Q24, you've got LEDs, pots, switches, and a USB TTL converter. And that's all been touched on in the previous videos. In terms of hardware, nothing's changed. So we've got prototype board, which I shall show you, and we have some power, programmer, LEDs and resistors, and switches and some other resistors attached to that. And this is the board I am using. This is where we left it last time. This is the board. This is the chip here. This is the programming cable to a PICKit2. I will show you a PICKit4, PICKit3 later on in this set of videos. LEDs. Those LEDs are touched through flying leads to these 4 points here. I've got the power attached in at 5 volts. I've also got the VDDIO2 attached as well. A potentiometer and an input switch here. They're all raised high and low as appropriate. So, what are we talking about? We're talking about memory. EEPROM is a type of memory. There are different types of memory. There's program memory, there's volatile SRAM, and there's, in this particular chip, 512 bytes of EEPROM. And so there's a memory map that's from section 9, of the data sheet, and that memory is actually partitioned up. It's up to the flash memory, and it's got other areas all listed down there quite nicely, and we're going to focus in on one of them. But the flash memory can be partitioned into application blocks, boot blocks, and an SAF block, and we will touch on all of those later on in the series of videos. So focusing in on the data, on this EEPROM section, or the data EEPROM, it's read-only memory in terms of it's there for a long time. I mean, it's seriously there for a long time. It's not like the other memory sections in the program memory. So this is electronically erasable program read-only memory. Now we're going to show you how to program it. And I am going to show you a few commands, and that equates to 10 pages, maybe more than that, of the data sheet. It's very simple to use in GC Basic. And you use this type of memory for relatively small amounts of data, the data that you can reprogram and erase and update, etc. So you can reuse this over and over again. So as I said before, we got an EEPROM block of 512 bytes, and the EEPROM is exposed with the variable chip EEPROM. So if you want to know the size of it, you can actually access that as a constant called chip EEPROM. The other ones are listed. Other constants are defined, chip words, SAF mem words, and chip RAM. They're all useful, but the one that we'll be looking at is chip EEPROM. And there are 3 ways that you can access EEPROM. There's a command. I'll bring my pen up. There's a command over here on the left called EPWrite and EPRead, and you pass those parameters of an address, and it's a relative address, so you send it 0 for the first byte, and in this case 512 or hexadecimal equivalent for the last. That would be 511 in reality. So this is an address and the data you want to send or the data you want to retrieve. And these are optional names. You could call them what you like. Out data and in data is what we're actually going to be using. and it will write data into the correct byte address in memory. Another way, I'm not really going to look at this one today, but it's used sometimes, is you can actually create a table that gets stored directly in the data memory. And the data memory is the EEPROM data memory, and you can write a list of 1, 2, 3, 4, 5, in this case 6 items, direct into memory. But you have to read our data sheets and read our help, and you create that table, and you must read that in your program. And so it does work. It works really good. It's very useful. However, we introduced a new way in 2023, which essentially you can just create what's called an EEPROM block, a name and a location, and then a set of data, and it will simply just write it into the hexadecimal file that is programmed. Bang, job done. We're going to look at that one today, and we'll see more of that style as we move through the videos. So, sample code, we're going to look through PPS, because we're going to have to put something out on the US art port. We're going to write some values to the EEPROM and read them back and see the results. Then we're going to write some other values using different techniques, and then we're going to see that actually on a program. I'm going to read the value back in, and we can actually see this. It's quite cool. And then I'm going to show you some sample code about using another constant and another way of using constants. Okay, so let's get into some coding. Editor's empty. Good. Let's go Control P and open up the next one. This is 140, showing EEPROM data to serial. Now, how much of this do I need to explain? Let's explain it all. So, chip option explicit. That's the chip specification, and we're running it at maximum frequency. PPS. This is going to set up the USART module on C.6. Now, hopefully that's connected. Good. This is the section that sets the baud rates and the other two constants. This is my layout, and I've been consistent. I recommend that you do this in every program. And a set of constants that make addressing the LEDs and switches support the potentiometer and the switch easily. So, with all that said, let's get into the real program. So what we're going to do is we're going to write a value to the EEPROM sequentially, all 512 bytes. And we're going to do that here. We're going to say the EEPROM address that we want to write to is 0 to the chip EEPROM. And that's quite important, chip EEPROM, because we said that's a constant. Zoom in. That's a constant. And that means that if I do it -1, it will take me to, it will effectively be 0 to 511, which is quite correct. Then we're going to have some fancy display stuff, and it's going to put it on the screen. I'm then going to output some data, and that's going to be 255 minus the address. And essentially, it's just going to write 255, 254, 253, 25, right the way through to 0, and then restart. It's just going to put some numbers into EEPROM for us. And here's the big command: EPWrite the address, that's EPROM address, and the out data. And to read it back in, EPRead in data. And I set it to 0 just for clarity. So I write the value out that I just calculated, then I read a value back in, and then I put it on the screen. Let's do that. Function key F5, I just pressed. I'll go into what I call Zen mode, which is this way that you can see everything that's going down. And what I haven't done is brought up a terminal. So function key F9, bring up a terminal. There's a terminal. Connect the terminal, and voila, it's just put it on the screen behind us. But do you know what? I'm just going to shuffle that over there a little bit. Clear that down. I might change the font size. We'll change it to 10 so we can sort of get it on the screen. Now in the program, it will do it again when I push the switch. There we go. That's cool. And as you can see, it's got a display, and that display says this is address 0, and this is the address of 16 bytes. And it went, I'll do it in decimal for you: 255, 254, 253, 252, 251, 250. And it wrote it backwards, which is fantastic. And when you get to 0 down here somewhere, it's restarting back at 255. And that's exactly what I wanted it to do. How do I know it's actually in there? Well, what I can do cleverly, I'm going to start PICKit2. So here's my PICKit. It's on the screen. It resets it quite correctly. And I'm going to read the EEPROM data. And as you can see, this is an external programmer. So I've read the file back in, and it says here that all these values are as expected: 255, 254, 253, etc. It works. Recap. Very simple. All the string handling you can look through in your own time. All the string handling is HC or something. This is just all the handling to get it all on the screen. The two key commands are EPWrite and EPRead. And as EPROM address is indexing through 0 to 512, it puts it in the right place. And this is just a calculation for us. So if you wanted to do random numbers, I put it in here for you. You could use random numbers, or you could have a fixed number. If you don't believe me, just put your own values in. It works. Control B. Showing table EEPROM data. Oh, what does this do? So this program, Control B. This program, same header. I've got a function called show EEPROM and do loop. So what's going on? It's going to put some data into the EEPROM directly. It's going to take it in the hex file. It's going to put it in the hex file, and when you program it, it automatically is there. You don't have to do this read and write because it automatically gets inserted into the hexadecimal file. Same for AVRs. So it says here an EEPROM block. It's got a name. You want to use that name later. 10. That's a hexadecimal value. Put it in location 10. And then here are some more values of 1 hexadecimal 11 to hexadecimal 16, and put that address 16. And it will automatically insert that into the chip for us. Now, what I can now do, the moment it's done it, I can read that back using my favorite programmer. And I'd expect to see those numbers in memory, and I do down here. Let me zoom in. Can I zoom in any further? I think I can zoom in somehow. Here we go. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's in hexadecimal. 11, 12, 13, 14, 15, 16 hexadecimal. It's put it in the right place. Fantastic. So a simple way, a very simple way of inserting information into a hexadecimal file is using the EEPROM and EPROM block. Now, what else is in here? Oh, look, it's a little formatting table, and it's using EPRead to put it on the terminal for us. So why don't we look at the terminal? And here it is in the terminal, and here is exactly what we saw in PICKitPlus, the same values. As I said, there's a third value called read table. Not going to cover that. You can go and look at that in slow order. But essentially, if I show you the hexadecimal file for this file, can Shift F7 will bring that up, or press function key F4. If we look at the bottom of this file, we can see that it has inserted something in our hexadecimal file, and it says at this address, that's an org, put this data, and at another address, 16, put this data. So we can see it's putting it in the right place. So there's two ways of doing it: EPWrite, EPRead. or you can just use the data block, your choice. What else I want to show? Control B. Finally, some constant stuff. Control B. Now the header is all the same here, and I'm essentially going to test that my program hexadecimal file is for the correct chip. Now, why would you want to do this? If you generate a hexadecimal file and you do not know it's for the right chip, it could still program. A programmer does not look inside of a hexadecimal file to find out if it is actually intended for the target chip. So if you know it's got a serial port on it, like we have, we can use that to test. And it's a useful test. It's a seriously useful test to know that your chip is the correct chip. So what this does, it says here, my target chip, if the target chip here, which is this string, is not equal to the chip name string, and that's a constant, it would actually put a message up. It would say this is not wrong, what chip it is intended for, or it is correct. Let's just see it in action. So it's going to test a string against a constant, and it's going to put a message on the terminal if it's correct. The microcontroller is correct. Program is intended for a 1626Q24. You don't believe me. If I said later on I wanted to make that for a Q27, different memory model, and all the other things, when I actually picked up that hex file, if I wasn't really good about my naming convention, this little program would tell you you've intended it for the wrong chip. Oh, there you go, wrong chip, intended for a Q27. Just a little way of exposing more constants. So you've got some constants that are strings, some constants that are numbers, etc. And later on, you can experience those yourself. I'll save that. So, back to PowerPoint. That's what I wanted to show you. Next, we'll be doing I2C with a serial, of course, to discover I2C devices attached to our little chip here. And at that point, we'll start drawing some graphics as well in the next couple of videos. We'll do I2C to start with, then SPI, then pulse width modulation, bit of external events, bit more memory, 6 more videos, and then we're at the back end of the set. But we're making great, if you got this far, you're doing a great job, and now enjoy.